Greetings, geologists, and we'll be talking about the Devonian period today. The Devonian marks the beginning of the late Paleozoic. So up until this point, you've learned about the early Paleozoic, which was made up of the Cambrian, Ordovician, and Silurian periods, respectively. So the Devonian, Mississippian, and Pennsylvanian, otherwise known as, by the way, the Carboniferous, and of course the youngest of the four periods, which is known as the Permian. All four of these periods make up what we refer to as the late Paleozoic. So as we get started, I need to set the framework for how the late Paleozoic differs from the early Paleozoic. The early Paleozoic was dominated by shallow epiric marine seas that covered large sections of cratons across the world, North America being no exception. However, during the late Paleozoic, it's not that we had the absence of seas, because we certainly didn't. We had two epiric seas that began in one that didn't finish yet. It would finish in the Mesozoic. But it was a difference in plate tectonics that made the late Paleozoic noteworthy to separate from the early. Starting in the Devonian, we get mountain building on both sides of the craton, meaning the Appalachian on the eastern margin and the Cordilleran on the western margin. It won't be long before we will see the same kind of impact when South America crashes into us from the south, and that will create the Ouachita orogeny. That doesn't happen in the Devonian period. Nevertheless, we see massive crustal deformation during the late Paleozoic, which is attributed to the formation of Pangaea. So you have to be thinking along the lines that we had Rodinia back during the Proterozoic, and it split apart, and the theme of the splitting apart, the rifting, was how do we bring those continents back together? So subduction zones around the world are going to form and start grouping Gondwanaland and Laurasia together. But a few key components have to occur to make these sutured continents, both in the northern and the southern hemisphere, before they can join at the hip a little bit later, towards the end of the late Paleozoic and the Permian period. You know that supercontinent as Pangaea. So as we start the journey through the late Paleozoic, we'll start with a very, very important period where lots of radiation in terms of evolution of organisms occurred, both in the marine setting and on land. So we have a lot to talk about because of some really important developments, and I will point out that one of those important developments has to do with soils and plants. So the Devonian period marks a lot of first of things that occur. For testing purposes, you really need to be focusing on when did things first appear, or when did they go extinct? When did a sea first transgress? When did an orogeny first get uplifted? So when you're studying for your quizzes, your midterm, your final, these are obvious questions. You just need to look at the storyboard of what happened throughout geologic past and piece together a story that makes sense. And always keep in mind that evolution has had a theme throughout geologic history, which was to evolve from primitive to more advanced. That doesn't mean the primitive guys go away, that they go extinct. It just means that more adaptations occur as the right circumstances in ecosystems and the niches that these organisms can live in, as those changes become a reality, the natural evolution of animals and organisms to fill those gaps and those niches occur. So natural selection plays a huge role in what works and what doesn't work. It's kind of like a big giant experiment. And some of the experiments don't work too well. Some of them are working just fine, and then all of a sudden some kind of catastrophic mass extinction shock event occurs, like we learned earlier in this semester. So let's talk about the ugly guy that's showing on your screen right now. He's kind of cool, isn't he? This is a placoderm and a very specific species, the most famous, I might add, that we'll learn about a little later. What makes this guy so weird? He's associated with the Devonian. While he really evolved during the Silurian, he was most prevalent and diversified during the Devonian period, which is one of the reasons the Devonian is referred to as the age of the fishes. Every major type of fish was in existence by then, so we'll be looking a lot closer at the variety of fishes that arrive when we get to the life forms. But just for a minute, I'd like you to think about how scary this guy would be. Imagine that his skull from base to top would be about from the ground to the middle of your thighs. And then imagine he could open his jaw so wide that an animal like another fish or a shark could basically be swallowed through these razor sharp jaws that he has right in here and right through here. And he would shear them with those razor sharp jaws and swallow them. This is not an animal I ever want to encounter. So if you told me to go back in time and have to go scuba diving in the Devonian seas, I'd say, you've got to be out of your freaking mind. There's no way I would do that, because he is entirely a scary guy. And there were lots of varieties of him. Just to clarify, not all placoderms were scary like this. Some of them were benthic organisms that just kind of hung out and scavenged at the bottom of the ocean. But anything that's as scary as this guy with an eye the size of this, and I'll let you in on a clue with evolution. When animals have big eyes like that, typically there's a reason for it. And you see those really big eyes that have a very important function, which is to spot prey. You'll see the same thing in the Mesozoic as we approach looking at reptiles and dinosaurs, specifically carnivorous dinosaurs. So let's continue to move on, and we'll talk about the major events that happened in the Devonian. Again, lots of stuff is fixing to happen, so kind of sit tight and get ready for an incredible roller coaster ride through the Devonian period. The Devonian period is marked by a symbol on the geologic timescale of a D, a capital D. It lasted from 416 million all the way through 359 million years ago. During this remarkable time frame, pretty much land gets colonized, the ocean radiates, freshwater habitats radiate. A number of important rock layers are deposited that are useful to us for economic gain and mineral resources. It is known as the age of the fishes. And this is a good look at why. By the way, this is the placoderm guy right here. In that picture, you can see some sharks, you can see some rayed fin fish, even some lobe fin fish, bony fish, and some of the others that we've learned about thus far. So let's take a look at some of these important events that occur, because they mark some very critical changes to where the continents are all headed to as we began the assemblance of Pangaea. In the Devonian period, we have two major cratonic events that occur in North America that are orogenies, mountain building events. One's going to happen on the eastern margin, which is the Appalachian Mobile Belt, and that's the Acadian orogeny. On the western margin, we're going to have a different type of plate collision where we have a subduction of an island arc that smashes into what would be the edge of the craton at that time and creates some new landmass to North America on the western side of our continent. And this orogeny is known as the Antler. Notice that they both begin with A, so it's very easy to confuse the two. I'm going to give you a way to remember them that's very easy using national parks. Acadia National Park is actually in the area of the Acadia Mountains, and it's located in Maine. That's the area where I want you to think about the Acadian orogeny occurring. So let's set the stage for what happened and how important it was. Europe is going to smash into North America, and it's going to smash in the northeastern states up around the Maine area all the way into Canada. When it does, that sutures the two continents together. Here's why that's significant. First of all, how do we know this happened? We still have some mountains left over today. I will give you that. But even though Europe is rifted away from North America, we have evidence in the form of rock record and fossils. The rock record is compelling, and here's how. There are two matching rock layers on either side of the craton, meaning our side or their side. So once we join at the hip, we're going to have these giant mountains that were big, and they're going to be like this. And when water starts to form, or during colder periods, you'll develop glaciers at the top of these alpine situations, and then as they melt and as natural hydrologic cycle occurs, rivers will go down both sides of this highlands. That means I should see deposition of the same rock material if the mountains were made out of the same stuff. So that means Europe should have a matching rock to what we have in North America, and we do. So let's discuss what those two rock layers are. In North America, the famous unit is called the Catskill Delta. It's a very red deltaic sands that's made up of fluvial deposits, and it's clear that it's fluvial based on the way that the grains of the sand looks, the fossil content that's there. We'll talk about it in just a minute in more detail. On the other side of the mountain that was facing the ocean, we see a thicker sandstone unit that was called the Old Red Sandstone. That's the Europe's equivalent of the Catskill red beds. Now their particular unit has more marine fossils, which makes sense because they were facing the large ocean at that time. We actually did have an ocean on our side, but it was a shallow epiric sea that actually was more of a deltaic situation where you could imagine almost the Mississippi feeding into the Gulf of Mexico, except there's a giant mountain there. So we're eroding down the same sediments. Let's take a look at how this occurred. Now, we had large volumes of volcanic material and oceanic sediments that were pushed onto the margin of Laurentia, which is going to be the new super northern continent that will join at the hip with Gondwanaland a little bit later. So as these land masses, meaning Europe and Asia, smash into us, meaning North America, then we're going to start to see this uplift occur. This is now metamorphosed material that's found in the present states of Maine, aka Acadia National Park, New Hampshire and Vermont, plus major parts of Massachusetts and Connecticut. Essentially, we added on landmass to the edge of the eastern margin of the continental United States and Canada. So you have to imagine that these rocks get smashed in a continental collision, continent-to-continent plate collision. It will always create massive thrust faulting and folding and deformation of bedrock. And that's exactly what happened in the Acadian orogeny, which uplifted the Acadian mountains. So here's the dynamics. You get this large mountain range. And can you see what I'm talking about? That really we're looking at this area right in here for the Devonian that got really impacted. So as we're connecting Europe to North America, that lifts these giant mountains, and the mountains are going to start shedding sediments along this section right here and subsequently on the ocean side right here, because we're kind of, Europe is smashing in this direction, so we got some ocean on this side right there. And this is important to note because the dynamics of what we find in both rock layers are very unique. So our side of the mountains produced this Catskill Delta system. Why is this such a famous rock layer? Well, let's get to that. The Catskill Delta was created by a series of rivers. So here are your mountains right here, and here are your meandering rivers that are going to flood into this shallow epiric sea. Well, we'll be getting into the sea shortly, but in short, it was the Kaskaskia. So the Kaskaskia sequence is going to be flooding the interior of the continent, and these are our highlands that we have currently. The importance of these deltaic deposits cannot be underemphasized. These particular sediments are known to trap crude oil and natural gas, specifically crude oil, which makes good common sense when you get trapped rocks, especially if you get folded and faulted rocks. folds like anticlines and synclines tend to trap in reservoirs of petroleum, fossil fuels, as well as groundwater for that matter. So this is exactly what's happened when we get these large mountains that formed and squashed into this side of the continent, and we now have a very large two-continent married up system. We're going to be shedding those sediments, and now I have the shallow marine sea on this side that can be depositing some of those important animals that are microscopic that help turn into fossil fuels. We have the perfect setting. So that's why this area is famous for the production of petroleum products. The deltas are made up of a very thick clastic wedge that's named for the actual mountains that exist there, called the Catskill Mountains. They're in northern New York. Now let me address how this works, because you need to know what a wedge is. When we get a mountain and the mountain forms and sediments, let's just say this is the mountain and the sediments are going to be deposited along this edge, they can't naturally grade out flat completely. They've got something that they're anchored up against. This anchoring process, where a mountain or even in a canyon setting like the Grand Canyon, that acts as a wedge. In other words, things have to build up against it. So that's exactly what's going to happen here, where you see all the red arrows that I put there. These are your deltaic deposits coming off of the highlands from fluvial deposits, and they're going to build up against these mountains. That's called a clastic wedge. So whenever we get a clastic wedge, that's an indicator of some form of mountain building, and it indicates to us that those sediments could not be graded out laterally until they pinch out. They're pushed up against something that was taller than they were. So where does the red come from that makes these rock layers so distinctive to their color and morphology and characteristics? It comes from the mineral hematite. So you've learned about that in physical. Hematite is a mineral that stains rocks and it oxidizes. So this gives us a hint and a clue that these rocks were deposited in a continental environment and not a marine environment. In the Acadian area, there was a dramatic climate shift in terms of sediments that proved this. We know it was global, but we had a definitive set of proof in terms of glacial deposits that told us the end of the Devonian was different from the rest. The early to middle Devonian were marked by worldwide warm empiric seas, and that was going to shift towards the late Devonian as we start to see glacial deposits. Specifically, we can see varves and dropstones, and that's what you're seeing right here. This is a big dropstone. As you learned in physical, dropstones are typically deposited in a glacial lake when an iceberg floats out to the lake and melts and drops a very large rock in the midst of fine-grained deposition in a lacustrine environment. So we know that these glaciers formed at the end of the Devonian in the Acadian highlands, and subsequently, surely, the other places around the world that had big mountains at that time. So remember I said that Europe had a matching set of rocks to the Catskill red beds, and they do. Their rocks are known as the Old Red Sandstone, and it is distinctively a similar unit lithostratically. It is a similar unit stratigraphically to the Catskill Delta. So understand that these two particular sediments were coming from the same source rock. The difference between the two is the fact that the Old Red Sandstone has a little bit different fossil assemblage. It has more marine fossils than what our version of it did, and it makes sense as to why. But the other characteristics match. They're the same. They're the same age, the same chemistry, the same type of rock. They share the same coloration. They're the same thing. So that's a piece of compelling evidence that suggests that Laurasia or Laurentia had actually come together and joined at the hip. So let's shift gears and talk about the west side of the continent. We're going to have mountain building over there. This is a completely different situation in plate tectonics terms than what we saw on the eastern margin with the Acadian orogeny. Instead, this is the Antler orogeny. What does that mean? This is going to be your Antler Island Arc right here, and this is the theme that you saw in the early Paleozoic, where island arcs were pushed into our craton by some type of mid-oceanic ridge beyond them that was separating, pushing the crust in towards the nearest continent. So in this case, the Antler Island Arc is going to come into the west coast. So let's set the stage here for a minute and understand that the west coast is not all bare yet. As to what you're used to seeing as the edge of the craton has not been sutured on yet. We're going to get some add-ons. This is one of those beginning add-ons. Also note that this is the first mountain building event we've had in the west coast for the entire Phanerozoic thus far. So during the entire Cambrian, Ordovician, and Silurian periods where we had these shallow empiric seas, this area was being blanketed with lots of marine sediments, deep water shales, carbonate limestones and dolostones, siltstones in the nearshore environment. Of course, at the shoreline, you would have seen thick sandstones, and certainly with the transgressive seas working their way towards the middle of the cratons, you would have seen thick sandstone units. That's all fixing to get squashed up as soon as this island arc smashes into what we would call Nevada area today and even parts of Idaho. So in Utah, it's going to squash into parts of Utah and Nevada. So this is going to cause some major uplift, and understand that all those marine sediments are going to get shoved up onto these Antler highlands. What happened in terms of the Devonian seas? This is a big story because we're basically going to hit the rewind button and go back to what Tippecanoe Sea did during the Silurian and repeat it with the Kaskaskia during the Devonian. The difference is the depth of the sea and how long it was in duration for. When it started, it's working its way towards the middle of the continent by the mid-Devonian, reaching its peak during the Mississippian. The Mississippian was the grandeur of the Kaskaskia Sea. What we see during this time frame is identical to what we saw with the St. Peter sandstone and the Ordovician as the sea began to encroach into the middle of the continent. We're going to see that same thing. We're going to watch that sandstone layer. It's very clean, it's mature, and if you recall, clean, mature sandstones are indicative of being a beachline deposit. The Oriskany sandstone is famous for this, and it's actually used as an important Devonian resource for glass manufacturing, for silica, and for even containing petroleum reserves and natural gas reserves. So, and it's an important rock layer in the sense that it represents a migration of a new empiric sea into the middle of our craton. As a matter of fact, it's very difficult in the field to differentiate the difference between Silurian carbonate deposits and Devonian carbonate deposits because they're so similar in character. So you have to find that unconformity that separates the two between the Tippecanoe sequence and the Kaskaskia sequence. So there's some difficulties with that process, and it's been one of those conundrums for geologists for some time is how can you tell the difference between the two? So you have to know more about the fossils. You have to be able to look and find out where you are in the stratigraphic column when you're in the field to know which rocks you're really looking at. So remember back to the Silurian when we had the Tippecanoe that filled up the Michigan Basin multiple times as water got stuck there because of the big reefs that kind of made moats around the basins. Well, the same thing's going to happen in the Kaskaskia Sea. The reefs are a bit different. They're more on the pinnacle. We did have barrier reefs, but we had lots of pinnacle reefs at this time. And it's just going to create a different age salt. What I mean by that is not necessarily just Devonian in age. It's going to be a little bit more mature. Salt goes through a process of change over time. And in this particular case, it gets to the most advanced form, which is potash. We'll look at that in just a minute. So these reefs restricted the flow of water into Williston Basin, and Williston Basin represents a large geographic area that looks at the parts of the Midwest, the northern Midwest, and the southern part of Canada. And so these reefs would have grown around this boundary where I'm kind of moving my marker right here, and they would have blocked out the water just like we saw in the Silurian, allowing for water to get trapped into the Williston Basin as the Kaskaskia regressed off of the continent. Even as it had minor transgressions and regressions, it would do the exact same repeat of what we saw in Michigan Basin. This would have been the types of corals that would have built around the perimeters of your Devonian-aged basins like Williston Basin. Now again, these are modern day coral reefs, so I don't want you to think that these species would have been present at that time. We would have had pinnacle reefs, we would have had some barrier reefs, but nevertheless, it still achieved the same purpose. So sediments like this would be filling in these basins and filling in the areas like Williston Basin. And this is a carbonate set of sediments in the Bahamas. So I want you to look at this. This is what's going to spill into that portion of these basins and create an important set of rock formations as well as evaporite deposits that are inside of these basins. So the Devonian aged evaporites that are famous and useful for intrinsic value are called potash, and over half of the world's potash comes from this aged rock, and specifically from Williston Basin. This is potash, and you're like, well, I don't see the salt. The salt's in here, and what's going to happen is they're going to extract this material out and get the actual potash, which is really the reddish material mixed with the white, and they'll extract it and make it into what's in your fertilizers. So potash is extremely important for agricultural use and for general landscaping use. So realize that the Devonian produced lots of potash while the Silurian produced lots of halite. Another important rock layer to discuss in the Devonian is the Chattanooga Shale. The Chattanooga, you need to think about it, it represents a different complete depositional environment that'll exist from the end of the Devonian to the beginning of the Mississippian. During the Middle Devonian, many regions that previously experienced heavy carbonate deposition began to transition. They produced coarser detrital sediments. During the Late Devonian, this would shift again and create a completely unique environment where we would see the widespread deposition of black shale layers known as the Chattanooga. It goes by different names in Canada. Nevertheless, we call it the Chattanooga down here. This is a look at that layer. It's not a really thick layer, but it's a very unique and useful layer for monetary purposes. We find these black shales are most prevalent from the cratonic margins to the Mississippi Valley, and especially from the eastern side of the continent. The same types of sediments are found on the western side that kind of grade out from western Canada, which makes sense from the same type of material that we just talked about a few minutes ago. These shale layers are about 30 feet thick at maximum and are very rich in conodont fossils. Back in my Brazos River Authority days when we were doing water quality monitoring, on occasion we would come across a lake. And that lake or river would have this appearance to it. And that was not a happy thing for us. First of all, the water stunk. Second of all, the chemistry was very icky. And what I mean by that is usually the pH was very acidic, everything was dead, it was dying, nothing could support life. Well, that's indicative of an anaerobic environment. Basically, the only thing that can live there are anaerobic bacteria that are helping break down what's dying. A natural process of life, by the way. So here's what we think happened to form the Chattanooga Shale. We think that detrital materials kind of slowed down coming off of the highlands, and we've created these shallow epiric marine settings where the ocean bottoms became anoxic. They lacked oxygen. And so we had these really productive microscopic animals at the top of the ocean that were photosynthesizing types of algae, like foraminifera, things like diatoms, things like radiolarians. These are the types of microscopic animals that you would expect to see. And this top layer would have been oxygenated, and these guys get a large algae bloom. We can see this in modern day lakes and rivers. So I'll just take a lake, for example. We get a nutrient load into a lake like Lake Waco. And Lake Waco produces an algae bloom. In years past, that would release a small oil that would cause a taste and odor issue. And now we've kind of resolved that by building a dissolved air flotation plant. So if you want to learn more about that, you've got to take in my environmental science class, and I take a tour there for my lab, and it's really fantastic to see how they treat this water. Nevertheless, we didn't have those treatment technologies back in the Devonian, right? So these animals were loving life at the top of the water until things went wrong. The chemistry of the water changed, they die off, and they sink to the bottom. That's going to immediately suck up whatever oxygen's there and create an anoxic conditions. And as they start to decay, these animals are going to be left undisturbed. They get buried pretty quickly. They're going to deplete all of the dissolved oxygen down there, and we're going to have this really crazy, weird shale deposit being laid down. So we can see this happen in modern day time, which is how we suspect it happened back in the Devonian. What's the significance of these dead animals? Well, let me show you. The significance comes in what they produced. Now, we think about uranium, you think about it being a metal. And while it's an ore, where it comes from is rather remarkable. It's usually created by the decomposition of dead microscopic animals, just like the situations we discussed. So this layer, this is the extent of the Chattanooga Shale. This is really a very useful shale unit for uranium. So it's mined extensively for that, and it also contains oil and gas. What a surprise, right? Because the right depositional environments to make them with the right dead animals to create the fossil fuels are there. So we find uranium all throughout the Appalachian Mobile Belt. We find it even throughout the Midwest here. And believe it or not, this area of Texas is known to produce it as well. Even the areas that we talked about up here for Williston Basin contain the same type of shale deposits. So the Chattanooga Shale is very valuable in terms of economic gain for what it provides in terms of a very useful mineral ore known as uranium. Let's take a break and we'll come back and discuss the life of the Devonian, and we'll talk about the plants and the organisms that made up the life that we'll see. So when you come back, we'll be talking about these remarkable life forms. And if you have not already, you need to read your chapters, and it's plural, for the pages that I've listed for the Devonian. Lots of stuff happens. If you don't have this background from reading, you're going to be kind of lost. And it's complex stuff. So get ready, and I'm looking forward to seeing you back for the second half of Devonian. Bye.